Hello and welcome to Engineering Physics 2P04 Lecture 13, Truss Problems. Now we're going to return to static equilibrium, this time looking at the internal forces inside structures instead of just examining structures from the outside. We're going to spend two lectures on this. The first one is about trusses, the second one is about frames. What is a truss? A truss is a member that only has forces applied via pins at its ends. So all of the forces are applied at the ends of the truss. There can't be any non-axial forces. It can either be in one of two situations, either in compression, meaning that the truss has been compressed, and if you were to let go of it, it would expand, so it's pushing out on the pins around it, or it could be in tension, meaning that it's pulling. It's been pulled into an extended form, and if released, it would compress, so it's trying to pull on the pins. The typical sign convention is we assign positive for tension and negative for compression. Ropes are kind of like trusses that can only be in tension. You can't push something with a rope. A frame is a more general member that can support torques and forces applied anywhere on it. It can have axial forces, transverse forces, and moments. We're going to deal with frames in lecture 14. Example problem for a truss is a problem from the Physics 1 DO3 exam. The truss ABCD is made of members with negligible mass forming equilateral triangles and supports a weight of 600 newtons at pin C. The truss is fixed at pin A and supported at pin D. Find the internal force in member BD and state whether this is a compressive or tensile force. First, a question for you. They mention that the truss is made of members with negligible mass. Why is that important? Well, if the mass of the members is relevant or non-negligible compared to the other forces applied, then there's forces on, say, member AD here, forces on this member that aren't just at the ends, and then strictly speaking, it's not a truss anymore. We'd have to analyze it as a frame, like we'll deal with in lecture 14. So all we're going to do is go through each pin and then do the write the net force on each one. So let's do the force balance equations at each pin, drawing the truss force as tensile by default. On pin A, we've got force in the x direction would be FAD plus FAB cos of 60 degrees. It's an equilateral triangle, so all the angles are 60 degrees, plus RAX. The usual assumption is to take the reaction force at A as pointing in the positive direction, and the vertical direction for its vertical reaction force. Point D can only have one of these vertical reaction forces, and in fact it has to be positive. You can't be pulling for this this kind of a joint. A, because it's a pin joint, can supply forces but no torques. So in the vertical direction at pin A, we've got FAB sine 60 degrees plus RAY. On pin B, you can try writing this one out yourself if you like. In the horizontal direction, we'd have FBC plus FBD cos 60 degrees minus FAB cos 60 degrees. And in the vertical direction, it would be minus FBD sine 60 degrees minus FAB sine 60 degrees. Sure enough, looks good. And similarly on pin D, and on pin C. Now you can just solve all of these equations with Maple, and that's primarily the way we're going to be doing it in 2P04. We have enough equations to solve for everything because we've got 8 independent linear equations. There's no forces squared or anything like that, or forces times each other, and there's 8 unknowns. So typing them in Maple and using the solve command will give a unique solution for all the unknowns. We'll do that explicitly later on for some of the more complicated ones. You could generate additional external equations by viewing the entire structure as a rigid body. This is sometimes a convenient thing to do if we just want one particular force. So in this case, we only want the force in member BD. Maybe we can speed that up. Instead of writing all of the pin equations, we just write the ones that we, some specific strategic ones, and then do the whole body as a static equilibrium problem itself. So for instance, if we were to say, okay, this whole truss is in static equilibrium, then the net torque on pin A must be 0. The reaction, because it's a pin joint, we can't actually apply a torque from the reaction forces. So that means that the net torque must be just due to the forces acting on the truss elsewhere. So we've got this force C, which is 1.5 members away. And we've got the reaction at D, which is 1 member away. So that tells us right away that we've got the length of the member, RD, minus length plus length cos 60, 600 newtons. So this lets us solve for what the reaction at D is. And then we can more quickly solve for the information that we're looking for. Without Maple, solving all 8 equations is not the fastest way to get the solution. So we'd want to go through the external forces and just use the some convenient tricks to solve that instead. Now this is a question from a Physics 1 DO3 exam, which is just a multiple choice question. So we're not going to want to spend the time to solve the entire truss to answer it. The members in the ideal truss below are connected by pins and have negligible mass. That's what tells you it's a truss. Mass M is suspended from the pin at C. That's okay, still a truss because it's just applied at the pin. Determine whether AE, this member here, is in tension, compression, or is a 0 force member. All right, the fastest way to do this is to think, okay, we've got this mass here applied. So looking at the reaction forces at E and D, they both have to be pushing up on the truss. If they weren't, then the member would fall, the truss would fall and or rotate. So that means that the reaction force at E is in the vertical direction. Then doing the force balance there, you can see that member AE, since we're pushing up from the reaction force, member AE has to be pushing back down on it for this pin to be in equilibrium, which means AE has to be in compression. And that's pretty much it for trusses. So in first year, you learn all the math that you really need to deal with trusses. In second year, there's just one other thing that you might do, which is kind of, it doesn't let you solve any additional trusses. It's just a different way of looking at things. You distinguish between the method of joints, which is what we've been doing so far, solving a truss by writing the force balance equations for each pin. Pin is also known as a joint. And this is what we've done so far. This is what you did in first year. In addition to that, you could use what's called the method of sections, which is to slice or section the truss anywhere that you like, and then say, well, the left-hand side of that and the right-hand side of it have to be in static equilibrium as well. So we should be able to use that to figure out the forces in the members that we sliced through by applying the static equilibrium of the body that's left on the left. So for instance, this one, what we could do is just imagine making a slice through here, so vertically where I'm drawing like that, and then you can say, well then this whole left-hand side has to be in static equilibrium itself, or maybe you could slice through right here and then say that the partial truss that you're left with on the left-hand side of that has to be in static equilibrium. This is a shortcut to finding some member forces that without having to go through and solve the entire thing. So I'm going to illustrate this by giving you an example problem. You can try this out yourself. First, it's a method of joints thing, and then it's a method of sections. This is the scariest problem I could find on the Engineer 2 P04 truss assignment. So this is a big, scary looking truss, and all you're going to do is the method of joints to find the forces in the members meeting at joint C, which would be these three, and the method of sections to determine the forces in members CD, DK, and KJ. So first, see if you can locate those members, and then decide where you would slice or section the truss in order to find those out. Okay, so you can actually make one section that goes through all three of those members, and that's this section right here. So there's KJ, there's DK, and CD right there. So if you were to section the truss vertically from where the mouse cursor is there, you'd get all the members that you're interested in. Then in the solution, we're going to look at the left-hand side of that. You could do the right-hand side and say that that's in static equilibrium, or the left-hand side. We're going to do the left-hand side, so give that a shot. Also try the method of joints for part A. Okay, you can solve the equations manually if you like, but you're going to save some time if you just type them into Maple, since that's what you're going to have on your test. So here's the solution to that. For both methods, the strategy that to really speed things up is to once again look at the equilibrium of the entire truss from the to figure out what the reaction forces are. So we know the forces applied internally, which are, or rather the forces applied in the middle of the truss from external applied forces, these 15 kilonewtons forces, and there's no forces in the horizontal direction except for this one horizontal force at A, so that has to be 0 because there's nothing to balance it. And then the reaction forces at A and F in the vertical direction here, we can figure out by using the torque balance equation and the force balance equation. Then we'll proceed pin by pin to get the forces that we're interested in. Let me just describe through this problem. So let's start at pin A. In the vertical direction, we can use RA and that to figure out what this force is. And then in the horizontal direction, we'll have this force and this force, but this one's known. So then we can figure out FAL, and that's that. Now, if we were to then jump to pin B, what do we know? We know the FAB. We don't know the force in BL, we don't know the force in BK, and we don't know the force in BC. So we've got 3 unknowns, and we'll only get 2 new equations, the force in the X and Y. So we can't jump to pin B just yet. Let's jump to pin L instead. Now, what are the unknowns? The unknowns are our tension in LK and tension in BL. So just 2 of them, and we've got our 2 new equations, so we'll be able to solve for that. Now that we know tension in BL, we can jump up to pin B and solve for the tensions in BK and BC. And then if we jump to pin C, we've got 2 new unknowns, 2 new equations, so we'll have all the forces around pin C solved for. Here's a view through that. Joint A, joint L, joint B, joint C. You can see that you got all of those equations written out, and then we can type them in Maple. To go to the next line here, I'm kind of writing them out one line at a time to make it look a little bit clean in Maple. What you do is you hit Shift Enter to go to the next line without actually executing the code. It's just something to help you type it out a little bit more quickly. So there's no actual line breaks in there, and Maple doesn't view this as the end of a line and give you an error. So you can execute that and it'll solve everything out for you. I put an evalf in front of that to make force evaluation as a floating point and to find this C45 as cos of 45 degrees because we're going to use that angle quite a lot. So just to save some time in typing it out. Cos of 45 is also sine of 45, so we don't need to define 2 of those. Finding all of that out, we get that TCD is negative, which means it's in compression, and similarly for BK, while and also for BC. And CK, the other one that we needed to know, is positive, so that means that it was in tension. Method of sections, if you haven't done that yet, then pause the video here and give that a shot. So here's the section that we should get. Think about why this is the section we want to take, and then what you want to do to solve for this is just apply that the left-hand side of this section. So what we're picturing here, which is the left-hand side of of the truss, the part of the partial truss that's left after sectioning it through those members that we want the forces of. We can apply that whole side is in equilibrium. And now you see the truss forces that we're interested in are external forces on this partial truss. So we can solve for those. Do we have enough equations to figure out all 3 of them? Well, let's see. We've got 3 unknowns. And because this is a partial truss, we can also use the torque equation on it. It's not just like a 0 equals 0. So we'll get 3 new equations, force in the X, Y, and the torque equation about Z to figure out what these new tensions are. Writing all 3 of those out, and using the original truss picture to figure out that theta is the arctan of rise over run, so 3/1. We can solve for what the truss forces are, what the members forces are, find that CD once again is in compression, 10.6 kilonewtons just like before, and we also solved for KD and KJ.